Welcome to my video on uniform circular motion. What I want to do in this video is look at motion that's in a circle rather than in a straight line. Here's going to be our car. This would be a good example. There's the back of it, and there's the wheel well, another wheel, the front of it. Okay, so here's our car. And we're going this way. Let's put some tires on it. And the tires are spinning, just like you would expect in a normal car. Here's our ground. Now, there's two types of motion occurring here. Basically, if you look at it, one is the linear motion, and that's just the car is moving forward, and we're going to call it at a constant speed. So in other words, we're out on the highway just going 70 miles an hour, whatever we're going on the highway. Now the tires are turning, so this is circular motion here on the tires as they turn. So there's two types of motion here. The linear is the car going forward, and then the wheels spinning. So what we want to look at here is it's called uniform circular motion. In other words, it's not accelerating or decelerating. Constant speed. That's the case we're going to look at. That's the simplest case. Now let's draw our circle here. Start labeling some of the points and trying to figure it out. This is going to be like our wheel, for instance. There's the radius vector, the radius out to the edge. Now we start at a particular angle, and this is our change in the angle on the position on the tire. And we'll call this distance S. This is how far the tire is going to be moving as a function of time. So the tire is rotating, and it changes the angular position over time. So let's start defining things. So the angular position is just the angle theta. Now we've got the angular velocity. We're calling omega, Greek letter omega, delta theta divided by time. So that's how far it moves over time. So the change in angle per unit time. And then the angular acceleration. Now in this case, it's going to be equal to 0 because we've got uniform circular motion, constant speed. But it could be if the car is either speeding up or slowing down, that would be non-zero, but that wouldn't be the case of uniform circular motion. So we're just looking at the case right now when we've got the angular acceleration equal to 0. But if the velocity is changing, we're speeding up or slowing down, this alpha does not equal to 0, and it's just going to be equal to the change in angular velocity divided by the change in time. So one equation, if we want to write the angular position, is going to be where we start at plus this angular velocity times time, and that's going to be in units of radians. And one thing to notice is depending on where you're at on the wheel, like you're there or there, your angular velocity is still the same. You're covering the same angle per unit time, but your actual displacement there is going to be greater than here because you're further out, your r is larger. And that goes back to S is equal to r theta. So the farther you're out on the wheel, the faster you're moving, your displacement is changing more rapidly. Now let's look at the difference between angular and linear measurements. So in linear, that's like the car moving forward. Then we've got angular, and then we'll look at the relationship. Try to tie these two together. They're closely related. One's in a straight line, the linear, so that's going to be our displacement, like our distance or our position, whatever variable we want to use there. And then in angular, we talk about the angle theta. And so our relationship here is the displacement along the edge of the tire or wheel or circle is just r theta. That's how far out we're out, and we saw that just a minute ago on the previous slide. And if we look at our linear speed, how many miles per hour, kilometers per hour, or meters per second, whatever the units we want to use here, the angular equivalent is the angular speed, and we put that as the variable omega. And we know the relationship between the velocity of the wheel on the outside, like its ground speed, is going to be omega times r. And then we will look at acceleration. And usually on a linear speed, it's just an a is a typical variable. Now what we want to look at is we want to look at this case, we're looking at the acceleration, if there is any. Here's r. It's called the tangential. We call that alpha of t, or a of t. So this is going to be the angular. And we're going to specify it's the tangential. Now, in the case of uniform circular motion, we know that that's 0. But in the case that it's not, say the car's accelerating or decelerating, then the tangential acceleration, this is out here on the edge of the tire associated with the velocity, is equal to the angular acceleration times the radius. So that's how those are tied together. But in uniform circular motion, alpha is equal to 0. So this is the case I just showed you here where we are moving faster or slower. Now let's look at centripetal or radial acceleration. Let's look at the case of a ball on a string. There's some games you can play. You can put a ball on a string over your head and whirl it around. So here's the ball, and we're going to make this our radius vector here. This is where the string is attached. It goes out here, radius r, and we're going to make our ball right here. There's our ball. That's going to have a mass of m. Maybe it's a tennis ball or a tether ball or whatever type of ball it might be. And it is spinning around over our head. So that's what the situation we're going to talk about now here. There is an acceleration, so there is acceleration, and this points towards the center. That keeps the ball from flying out into the yard. So that's the acceleration of the string, essentially, the force the string exerts on the ball. And this exists even when we have uniform circular motion. In other words, the speed is constant. So in circular motion, there's going to be 3 accelerations. We're going to have the one of the radial acceleration, or the angular acceleration if the wheel is speeding up or slowing down, and then the tangential acceleration, which is associated with the outer edge on the wheel or circle, its relative speed, relative like to ground speed. And then we've got this centripetal acceleration, which pulls a circular object inward, like a ball on a string. So we can say the circular or the centripetal acceleration is the velocity squared over the radius, which is just equal to omega squared r. And I just did the substitution, v is equal to omega r. So that's going to be one of our important equations right here. Centripetal acceleration is the velocity squared divided by the radius, or it's the radial velocity squared times the radius. Now let's look at centripetal force. So we're going to use Newton's second law. I've got a video on this. This tells us the force is equal to the mass times acceleration. Now then, centripetal force, this is the force that holds the ball in its motion, a circular motion around the string. That's going to be the tension on the string. It's mass times the centripetal acceleration, mv squared over r, which is equal to mass omega squared r. So that's going to be our equation for the force, essentially holding the ball in place so it doesn't fly off out into the yard or wherever it's going to go. So this is going to be the net force. It's going to be pointing inward. It keeps the ball from flying off. It keeps the ball moving in a circle. So that's the force acting on the ball, keeping it moving. And one last topic we'll look at here is called the period and frequency. So in uniform circular motion, it's periodic. There was the case of the tire on a car, goes round and around. And we call this period, T, is equal to the time for one revolution. How long does it take the tire to rotate? And this time is going to be equal to pi over 2 divided by the angular velocity, and its units are going to be in seconds, because it's just a time. Now another quantity related to this is the frequency. And this is like revolutions per second. And a lot of times you'll see this in RPM, or revolutions per minute. So we have to convert. But the SI would be in revolutions per second. But a lot of things we'll see in RPMs, like in a car, like on your tachometer, tells you how many revolutions per minute, RPM, that your engine is turning. So remember what units you're dealing with. So the frequency is just 1 over the period. And that implies omega is equal to 2 pi over t. We know that from this relationship we just wrote up there, just changing it, the t, the period, and the angular velocity, that's equal to 2 pi f. So once again, this is a good equation to remember. You'll see that a lot. Well, thank you for watching. Hope you learned a little bit about uniform circular motion. And thank you again.